Hello everybody. In this video we're going to be beginning chapter 11, probability. Specifically, we're going to start with topic 11.1, randomness and probability. Probability is precisely the study of randomness and uncertainty. Now, what does random mean? In probability, random is in reference to events that are not perfectly predictable, but that have long-term regularities that can be described and quantified using probability. Examples of this would be flipping a coin and getting heads, as you can see in figure 11.1, which is the number of flips on the x-axis. And notice that as the number of flips increases, the probability of getting heads approaches more and more, 0.5 or 50%. Likewise, in figure 11.2, we can see that this is a chart of the probability of finding the traffic light green, which is about 30% over time. Actually, it should be about 33%. Notice that this is due to the fact that you have three different light colors. Therefore, the probability of finding it green is about 1/3 in the long term. So in statistics, when we produce data by sampling randomly or even by experiments, the laws of probability enable us to answer the question, what would happen if we do this many times? Okay, so now we're going to go over some basic definitions. An experiment is the process by which an observation or measurement is obtained. A random or chance experiment is an experiment where there is uncertainty concerning which of two or more possible outcomes will result. For example, if you flip a coin, you don't know whether you are going to get heads or tails. A description of a random phenomenon in the language of mathematics is called a probability model. For example, if we describe flipping a coin, it has two parts, a list of possible outcomes and the probability for each outcome. The sample space U of a random experiment or phenomenon is the set of all possible outcomes. For example, for one flip of a coin, the sample space is going to be heads, tails, or simply H, T. So next we have example 11.1, and it says, flip a coin twice or two coins once and record the results. What is the sample space? So let's recall that the sample space U of an experiment is the set of all possible outcomes. So what would be all the possible outcomes? We could get something like this. We could get heads, heads. We could get heads, tails, or we could get tails, tails, and tails, heads. So this would be the sample space U. So let's continue with example 11.2. And it says, when rolling a standard six-sided dice, what are the sets of event A, observe an odd number, and event B, observe a number less than 5? So event A says observe an odd number. So that would be just a list of the odd numbers, right? So that would be 1, 3, and 5. Whereas event B says observe a number less than 5. So that set would be the numbers that are less than 5, which are 1, 2, 3, and 4. So we continue with example 11.3. And it says, flip a coin 3 times and record the results. Show the event observing 2 heads on a Venn diagram. So notice that they're introducing set theory here. If you flip a coin, you have 2 possible outcomes. And if you do it 3 times, then this would be 2 to the 3, which is a total of 8 outcomes. The sample space would have 8 possible outcomes. We can easily verify this using a tree. Notice that we can get either heads or tails, and then after that we can get either heads or tails, and then here we can get heads or tails again. Here we can get heads or tails, and then just the same process again, right? Heads or tails, and then heads or tails, and then heads or tails. They want us to represent this on a Venn diagram. So a Venn diagram is normally a rectangle. So we draw a rectangle, and in the rectangle, normally on the left-hand side corner, we would write U, which means the sample space. Some people use omega instead of U, but we're going to stick to U for this purpose here. So what are the possible outcomes? Well, notice that we can use the tree for all the possible outcomes. So we could say heads, heads, heads is one possible outcome. So heads, heads, heads. We would also have the possibility of heads, heads, tails, heads, tail, heads. We also have heads, tails, and tails. Also tails, heads, heads. And we have tails, heads, tails. We also have tails, tails, heads. And finally, tails, tails, tails. So here we have all the 8 possible outcomes. Since they want us to show the event observing 2 heads, notice that I already put them conveniently here in the center, and I can just draw a circle, or I should say an oval shaped thing here, that encloses the 3 possible outcomes where we would get 2 heads. So in the next slide, you're going to find a few illustrations of some useful set theory results. So first we have A union B, which is represented by this green region here, where we have sets A and B in union. There is A intersection B, which is this green section where A and B intersect. Now, before understanding the third one, we need to look at this diagram I have here to the left, which is A minus B, also written with A slash B, and that is represented by this pink area here. It means set A minus set B, or minus the part of set B that is in A. This third diagram we have here is A symmetric difference B, and that is equal to A union B minus the intersection of A and B. So notice that we have subtracted the intersection part, and it is now in white for A symmetric difference B. This A prime, this represents the complement of A, or all of that which is not A, as you can see in the diagram. Here we have A intersection complement of B. So the complement of B would be everything that is outside of B, but this would be the intersection of that with set A, as we can see in the green part here. This is complement of A intersecting B. This is A union complement of B, as we can see here. So it's A united with all the complement of B. And then the last two are what are known as the De Morgan laws. And they say that A complement union B complement is equal to the complement of A intersection B. And then you can logically deduce this yourselves, as you can see here from the diagram, right? If you take the complement of A and the complement of B and put them together, it's the same as the complement of the intersection of A and B, as you can see by this white part in the illustration. And this other one is the other De Morgan law, which is just the opposite of the previous one. If you have complement of A intersecting complement of B, that is just the same as the complement of A union B, as we can see here. Very well, so next we're going to talk about tree diagrams, tables, and grids. So let's suppose that we have a 2-stage experiment to check the blood types of patients, where first we identify the type of blood, and then we classify the RH factor as positive or negative. So these events could be represented on a tree diagram quite similarly to how I did it in the previous example. So notice that first we have the blood types, which are A, B, AB, and O, and then plus and minus for each blood type. And then in the last column, we're going to end up with the actual sample space, which is the set A positive, A negative, B positive, B negative, AB positive, AB negative, O positive, and O negative. So the same events can also be arranged in a probability table or by using a two-dimensional grid. So notice that in table 11.2, we have a probability table with the blood type in the columns and the RH factor in the rows, and we get the combination of all the blood types with their positive and negative RH. And then here in figure 11.6, we have a 2D grid for the probability of blood types as well. So notice that we have the plus and the minus in the horizontal and the blood types represented in the vertical. So next we're going to do example 11.4, and it says, two unbiased tetrahedral dice with sides numbered 1 to 4, one blue and one yellow, are rolled. List the elements of the following events when both dice are thrown. So event T, it says 3 is face down on at least one dice. So that means that the 3 can repeat. So notice that here to the right, I have the rows representing blue in this 2D grid, and the columns are representing yellow. So this is a guide that we can use to find the elements. So what are the possible combinations? So for T, we're going to do yellow, blue. So it would be 1, 3, 2, 3, 3, 3, because it says that at least on one, and 4, 3. So what would be the other cases? Well, let's get 3 for yellow. So 3, comma 1, also 3, comma 2, 3, comma 3 we already have. So finally 3, comma 4. So these would be the elements of event T. Event B says the 3 on the blue dice is face down. So that is only when it is the blue dice. And that would be then 1, 3, 2, 3, and 4, 3. And finally, event S, which is the sum of the face down faces on both dice, is 6. So the sum is 6. Notice that that would be 2, 4. It would be 3, 3, and 4, 2.